Let's take a moment now to think about how everything we know about fluid mechanics can be used to help us on this journey through understanding heat transfer. The specific question that we're going to ask is, what is the fluid mechanics analog of Fourier's law? With Fourier's law, we see here that we have a heat flux, Qx double prime, which is related to a temperature gradient. So a gradient in temperature drives a heat flux. The quantity which is related to this from fluid mechanics is from Newton's law. We see that we have a gradient in velocity given by dvx dy, and that this gradient then drives momentum flux. So there's a clear parallel between Fourier's law and Newton's law. In Fourier's law, it's a temperature gradient. In Newton's law, it's a velocity gradient. In Fourier's law, it's a heat flux, and in Newton's law, it's a momentum flux. This analogy, though, is not perfect. The thermal conductivity and viscosity mu have different units. So we should try now to restate these gradients in terms of conserved quantities, and that will help us make this analogy even more perfect. So we're going to take temperature and now restate it as energy. And in doing so, we will see that we will achieve our goal of getting parallel units between Fourier's law and Newton's law. So we take the temperature T, we multiply it times rho Cp as shown here, and we get an enthalpy H. We apply that in the equation below, and we find that Qx double prime equals minus alpha dH dx. Alpha here is the thermal diffusivity. It is this ratio of Kx and rho Cp. We can do the same thing now with Newton's law, making the velocity into a conserved quantity, momentum. This requires here multiplying the velocity times rho, so that we end up with rho Vx, the momentum. If we apply this now to Newton's law, we find that we end up with stress equaling minus nu times d rho Vx dy. Nu here is the kinematic viscosity. It is the ratio of the viscosity mu and the density rho. And what is neat here is that alpha, the thermal diffusivity, and mu, the kinematic viscosity, in fact have the same units. They have units in meters squared per second. So when we express everything in terms of conserved quantities, the parallels between the new formulations of Fourier's law and Newton's law become even stronger. There is a clear analogy between thermal energy moving and momentum moving. It is, however, inconvenient to measure enthalpy, and we instead, in this course, will generally use temperature. But there are many lessons that you can take from everything you know about fluid mechanics to help you solve problems in heat transfer.